Okay, so we're starting hyperbolas today. So we've done circles, we've done parabolas, we've done the ellipse. Now we get to the hyperbolas. I still think that the parabolas tend to be the most difficult ones to deal with. For my students, hyperbolas tend to be a little more difficult than ellipse, but nowhere near parabolas. Okay? Especially since we're dealing with a very similar equation to our ellipse. Okay, so the hyperbola. Okay, hyperbolas we do absolutely use, especially in physics. We deal with nozzles. Nozzles are basically hyperbolic in shape. So you use them in architecture, power plants, the chimney, which is just basically a big nozzle to help cool the steam that's coming out of a power plant. We see it all over the place, especially in our energy sectors. Do we deal with fluid rates? When we deal with drilling, especially oil and gas, if you're going to be doing any kind of drilling, or especially when I forget what it's called, the sludge that they pump back into the system to create pressure. Some kind of sludge, I forget the name of it, but we definitely will be using nozzles if you're going into some kind of oil and gas or chemical engineering. Okay. Now, I think the coolest part of parabola or hyperbola, we'll talk about in just a minute, deals with aerospace. Okay. Now, what is a hyperbola? Just like the ellipse is the distance is the sum is a constant, and a hyperbola though is a set of all points where the distance is a constant. It's a distance from the 2 points we call the focus. Okay, so an ellipse, the distance between the focal point to any point on it, the sum stayed constant, and a hyperbola, the difference stays constant. Okay, so if you look at this point here, say we were talking about this point here, this point to that point, the difference is going to be constant, not the sum. Okay, so it's slightly different. Now, the other thing is the hyperbola makes the hyperbola a little bit more difficult is that all of my other shapes, I've only had to draw one curve. Circles, parabolas, ellipse. The hyperbola, we've got two. But, and it's got asymptotes, so it makes it a little bit more difficult. But I'm going to show you an easy method for that. Okay, so one of the aerospace deals that we deal with when we talk about hyperbola is, of course, that phenomenon of sonic boom, okay, or the sonic shock wave. When a vehicle crosses that threshold of the speed of sound, when a plane actually flies faster than sound travels, there is technically a physical barrier that crosses, and when it does that, it creates a large boom that can be heard for miles. Okay. The Concorde used to do supersonic travel across the Atlantic from basically New York to Europe. And one of the reasons that it was grounded was because people would complain every time it would take off, they'd hear this giant sonic boom, and it was starting to get upsetting. I mean, it's so loud and so powerful, it can shatter glass and do damage. So it is a basically physical barrier. Okay. Now, one of the coolest parts is you can actually see a plane before you hear it. So if a fighter plane in this picture, if you're sitting in your house and you look up, you'll see the plane, but you can't hear it. That's because the wave is actually back here. The sound wave is behind it. So you won't actually hear it until it passes you, which is kind of neat. Also, when it breaks the sound barrier, it does actually create a concussive wave, and it can create basically clouds. And you can see this is a plane actually doing that, breaking the sound barrier. And you can see from the front, it's kind of like got a circular shape, but from the side, you can kind of see that hyperbolic shape. It's pretty neat. So trust me, engineers, there's some really cool stuff that deal with conics. Okay? All right, so let's get to the math. So hyperbola, general rules. X and y are both squared, just like our circle and our ellipse. The equation always equals 1, so very similar to our ellipse. But the equation is always minus. It's always either y minus x or x minus y. Okay, where the ellipse is always positive, the hyperbola always has a negative sign in it. Okay, a squared is always the first denominator, so that's one of the major differences. Okay, in the ellipse, a was always the bigger one, but in a hyperbola, a is always the first denominator. Okay, the equation for c is a squared plus b squared. It is the Pythagorean theorem, unlike the ellipse. C is the distance from the center to each foci on the major axis. A is the distance from the center to each vertex on the major axis. Now, B is the distance from the center to each midpoint of a rectangle used to draw the asymptotes. This distance runs perpendicular to the distance A. Okay, so it's like our minor axis. Okay, the major axis has a length of 2A. Eccentricity is basically how long it gets looking like a circle. Okay. X squared is the first term, then it's a horizontal hyperbola, but if y squared is the first term, then it's a vertical one. So in an ellipse where it determined, the denominators determined whether it was vertical or horizontal, a and b moved. In a hyperbola, a and b stay the same and x and y move. Okay, so if the first one is y squared, it's vertical. If x squared is first, it's horizontal. For my kids, this is your code. H4P3RB0L4. H4PRB0L4. Now, the center is in the middle of the two vertices and the two foci, just like all the others. The vertices and the co-vertices are used to draw the rectangles that form the asymptotes. So we will use A and B, but not in the same way. We don't have a true co-vertices, but the co-vertices, we use that point to help us draw the rectangle to draw our asymptotes. And the vertices are the midpoints of our rectangle. And the co-vertices are not really labeled because they're not actually part of the graph, but we use the idea to draw it. Okay? So, the hyperbola that's horizontal looks like this. Okay? And again, we know it's horizontal because x squared comes first. So in a hyperbola, if my x squared comes first, so if it's x squared minus y squared, the hyperbola opens up left and right. That's what we mean by a horizontal major. Okay? And these are the equations for the vertex, the foci, and the asymptotes. Okay? Notice that the asymptotes start at the center, that's why we have h and k, and then the slope comes from a and b. Okay? Now, if it's a vertical hyperbola, that means that y squared comes first. Okay? And that means that it opens up and it opens down. Now, I use this picture specifically to show you really it doesn't matter which one comes first, A or B. Okay, what matters is that it's vertical because y squared comes first. And again, vertices, foci are basically the same as an ellipse, vertical ellipse. The difference is going to be that asymptote. Okay? So we're going to work a problem real quick. So this is our hyperbola. How do I know it's a hyperbola? Because I have x squared and y squared. It's equal to 1, and there's subtraction going on. I also know it's a horizontal one, because x squared comes first. Okay? So we're just going to find our information just like we did with our ellipse. So if you have your formula chart, you know your center's at h and k. So this is h, this is k. So my center's at 1, 2. Okay? Now, my foci. My foci from the formula chart are h plus or minus c, comma, k. That's what my formula chart says. Okay? Now, A is 2. Because remember, A is always the first one in a hyperbola, B is always the second one. So A is 2, B is 4. We're going to need C, which is the square root of A squared plus B squared, which is the square root of 20. Okay? So my foci are at 1 plus or minus the square root of 20, comma, 2. My vertices are h plus or minus a, comma, k. And in this case, h is 1, plus or minus a is 2, comma 2. My asymptote equation is y equals k plus or minus b over a, x minus h. So here we go. Y equals k is 2, so it's 2, plus or minus b is 4, a is 2, x minus 1. Okay, there is all of my information just basically taken off a formula chart, just like what we've done with ellipse. Okay, so let's graph this thing. So our center is at 1, 2. Here's our center. Our vertices, 1, 2 this way, 1, 2 that way. That's my vertices. Okay, now I'm going to graph my co-vertices, the points, using B. So if my vertices are left and right A, my co-vertices are up and down B. So 1, 2, 3, 4. I'm not going to label them with anything. I'm just going to put those points there. Okay? Now, I'm going to use those points to draw a box to do my asymptotes. So I'm going to make a dotted rectangle using these 4 coordinates. Okay? Like that. Now, I'm going to create a dotted line, an asymptote, using the corner of those. Okay? So from corner to corner, like this. There's one of my asymptotes. Okay? And then this one, it's not. It's not cooperating with me. There. From there to there. So these are my asymptotes. Now you could have, if you wanted to, just actually use the slope. Since my slope is 4 over 2, which is 2, I could have gone up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Okay? And the same thing and drawn all these points. But it's easier just to use that box to create those asymptotes. Now, to draw your hyperbola, now that you have those asymptotes, your hyperbola starts at the vertex and then comes up and follows the asymptotes. So it comes down here, follows that asymptote. Starts at the vertex, follows the asymptote. Starts at the vertex, follows the asymptote. And there's our hyperbola. Okay? So basically we're just finding the center, using A and B to create this rectangle, draw our asymptotes from corner to corner, and then starting at the vertex, follow them. Okay? And that's it. Now, the truly craziest part is that if I had just changed this to plus, this is basically an ellipse. This rectangle right here actually represents, if you do the inside, represents the ellipse with the same information. It's pretty neat the way it works that way. Okay, but that's hyperbola.